Last editions of Environmental Economics, I opened with the story about Easter Islands by Brander and Taylor. This year, I removed Brander and Taylor from our reading list because Misha Veldhuis pointed me at a reinterpretation. Still, I'd like to start with the version of the story I told last year. Easter Island is one of the most isolated inhabited islands in the world, being over 2,000 kilometers away from its closest neighbor, the Pitcairn Islands. By the time of European arrival in 1722, the island had no trees, a poor population of about 3,000 people, and a few hundred Maui statues scattered along the coastline. The famous statues, each carved from a single massive stone, were puzzling to the European discoverers, because the islanders that were met by the Europeans seemed unable to support an artisan class, nor move the monolithic statues of up to 86 tons. The mystery of the Maui statues invited some wild origin stories over the years, with some speculating that they were remnants from a civilization of the mythical sunk continent Atlantis, or even that they were extraterrestrial. Brander and Taylor proposed a plausible alternative explanation, that the statues were created before Easter Island's population collapsed. Brander and Taylor describe on page 121, recently discovered evidence suggests that Easter Island was first settled by a small group of Polynesians about or shortly after 400 AD. The pollen record obtained from core samples and dated with carbon dating methods shows that the island supported a great palm forest at this time. This discovery was a major surprise given the treeless nature of the island at the time of first European contact. Page 122 continues, a noticeable forest reduction is evident in the pollen record by about 900 AD. By about 1400, the palm forest was entirely gone. Population probably peaked at about 10,000 sometime around 1400 AD and then began to decline. Brander and Taylor point out that not long thereafter the island's first weapons appear in the archaeological records. Continuing the quote, carving had apparently ceased by 1500. At about this time, a new tool called a mata enters the archaeological record. This tool resembles a spearhead or dagger and is almost certainly a weapon. I used this grim history of the Easter Island as an introduction for the Malthusian catastrophe. But more recent studies suggest that no such population collapse took place. The review by Bregman, based on the work of Boersema, also cast doubt over the mata being a weapon. The deforestation of Easter Island did take place. The alternative explanations offered are that the trees were used to transport the statues and that deforestation was likely worsened by invasive alien rats. Bregman concludes that we should reinterpret the history of Easter Island as one of human ingenuity. While maybe not a perfect example of a Malthusian catastrophe, we return to the deforestation story later. But first, let us talk about Malthus's theory. Malthus is perhaps the most debated economist of all time, as we can see from some recent headlines. 7 billion reasons why Malthus was wrong, Malthus the false prophet, new limits to growth revive Malthusian fears, and the last, limits, why Malthus was wrong and why environmentalists should care, is the title of a recent book by Callas, a leading scholar in the degrowth movement. I will read some quotes of this work later. In his essay on the principle of population, Malthus describes that population, when unchecked, increases in a geometrical ratio, that is exponential, for example 1, 2, 4, 8, 16. Subsistence increases only in an arithmetical ratio, that is linear, for example 1, 2, 3, 4, 5. A slight acquaintance with numbers will shew the immensity of the first power in comparison of the second. Brander and Taylor translate this for us as Malthus argued that increases in real income arising from productivity improvements or other sources would tend to cause population growth, leading to erosion and perhaps full dissipation of income gains. He also suggested that population growth might overshoot productivity gains, causing subsequent painful readjustment. Malthus warns that if population is not kept under control with preventive measures lowering birth rates, the population will outgrow the carrying capacity of its environment and collapse through higher death rates. The latter mechanism is also known as the Malthusian catastrophe. Brander and Taylor point out that Malthus was not a fatalist. He believed that enlightened public policy could reduce population growth, contemplating both contraception and moral restraint as mitigating factors. Malthus, his theory, led the UK to keep census data through the British Census Act of 1800 and is said to have influenced both Darwin and Russell Wallace, the pioneers of evolutionary biology. However, more recently, Malthus seems to have fallen from grace in mainstream economics. Critics point out that the assumption of linear growth in food production is flawed and that the assumption that population increases exponentially does not hold either as countries get richer. Indeed, countries with higher incomes have lower birth rates, and during the last 2 centuries, food production has grown faster than the population, although not without adverse effects. For example, claiming more land for agriculture, fertilizer and pesticide use, and industrial fishing all contribute to the loss of biodiversity. In explaining his theory, I used the concept of the carrying capacity of an environment. Even though the term may not be attributed to Malthus directly, it is in line with the spirit of his theory. Verhulst introduced the concept mathematically in his Notice sur la loi que la population suit dans son accroissement, or essay on the law that a population follows in its growth. Let us consider his formula for a moment, where the change of population over time, noted here as dn over dt, is equal to some positive constant growth rate r times the size of the population times this 1 minus n over k. Here k is the mathematical expression for the carrying capacity. When the population is smaller than the carrying capacity, that is n over k is smaller than 1, meaning the total term is positive and the population grows. As the population approaches the carrying capacity, growth slows down and ceases as soon as the population has reached its maximum size, given the carrying capacity. Yet there is little that guarantees a smooth path as just depicted. It is also possible that the population overshoots the carrying capacity, readjusts, overshoots again, etc. It is also plausible that overshoot may irreversibly reduce carrying capacity in the process. Note that this figure is merely a thought exercise to illustrate this possibility. More realistic models would make K a function of stocks of natural capital, education, technology, and other relevant factors. Malthus, his ideas, had a revival when Meadows and colleagues published a study called Limits to Growth in 1972, in which they presented simulations of the consequences of exponential growth with finite resources. Their simulations included relations between the world population, food production, industrialization, resource depletion, and pollution. In Callis, his words, limits to growth inherited the logic of Malthus, with economy taking the place of population and resources that of food. The limits to growth simulations are nearly 50 years old by now, and recent analysis by Turner and Alexander, presented in The Guardian, has matched indices to their predictions. The limits to growth baseline business as usual scenario predicted that the population overshoots the global carrying capacity and starts to collapse in the next decade, unless we would take serious action on controlling our resource consumption. Leaving aside how to construct and compare indices such as industrial output or service per capita, the displayed figure shows how the baseline scenario matches the data so far. The figure plots the predicted values in dotted lines together with realized values in bright solid lines. In general, the simulations of the business as usual scenario seem to match the observations rather well so far, with the simulations often being somewhat on the pessimistic side. Yet the real test of these predictions comes only in a few years, and we should aim to prevent the occurrence of such a collapse on a global scale. Perhaps the most famous critique on the limits to growth came from the Nobel laureate famous for growth models, Robert Solow. In his 1973 article, Is the End of the World at Hand?, Solow wrote, "There is at least one reason for believing that the doomsday story is almost certainly wrong. The most glaring defect of the forest meadows models is the absence of any sort of functioning price system. I'm no believer that the market is always right, and I'm certainly no advocate of laissez-faire where the environment is concerned. But the price system is, after all, the main social institution evolved by capitalist economies, and to an increasing extent socialist economies too, for registering and reacting to relative scarcity. There are several ways that the working of the price system will push our society into faster and more systematic increases in the productivity of natural resources. Higher and rising prices of exhaustible resources lead competing producers to substitute other materials that are more plentiful and therefore cheaper, to the extent that it is impossible to design around or find substitutes for expensive natural resources. The prices that contain a lot of them will rise relative to prices of other goods and services that don't use up a lot of resources. Consumers will be driven to buy fewer resource-intensive goods and more of other things. All of these effects work automatically to increase the productivity of natural resources, i.e., to reduce resource requirements per unit of GDP. There may be some merit to the mechanism Solow described, yet it does by no means guarantee some optimal use of natural resources. And while the non-existing population collapse on Easter Island can be considered a story of human ingenuity, it is still a tragic story of lost carrying capacity with the extinction of Easter Island palm, Pachylocos disperta, and possibly other endemic species. You may have wondered why Easter Islanders did not take measures to protect their natural resources at some point. Brander and Taylor offer the following explanation. It is even possible that individual islanders did not recognize that depletion was taking place. Although the forest disappeared rapidly by archaeological standards, change was slow over the course of an individual lifespan. Typical lifespans for those who survived infancy would have been in the order of 30 years. And even during the most rapid depletion, the forest stock would have declined by no more than 5% over a typical lifespan. Some of you may have already recognized the parallels with climate change, where the 40% increase in the atmospheric concentration of carbon dioxide over the few generations since the Industrial Revolution may not seem enormous from the perspective of any individual generation, but this change is epic by geological standards. The human impact on the concentration of greenhouse gases is exemplary for a much larger set of influences over natural processes. Recently, part of the scientific community started adopting the term Anthropocene to describe a new geological epoch during which human activity has come to dominate several global natural processes. Crutzen introduced the term by referring to our impact on land use, the prevalence of river diversion, and the share of fish stock used for human consumption, among others. This realization that humanity has a globally measurable and increasing impact inspired the latest influential contribution in the Malthusian tradition by Rockström and colleagues. Rockström and colleagues proposed to establish 9 planetary boundaries for the impact of our economic activity and suggest parameter values for 7 of these. For example, the proposed threshold for climate change is set at an atmospheric carbon dioxide concentration of 350 parts per million. I'm not sure about the latest values, but ever since 2016 it is well over 400. The current rate of biodiversity loss and disturbances to the nitrogen cycle are also thought to be outside of safe boundaries.